Separation of variables is a fairly stock topic covered in a PDE course. I don't particularly like the method as an approach to solving PDEs because it masks a lot of the underlying algebra that is really strongly related to other topics in a typical DE course, like eigenvalues and eigenvectors. So what I'm going to do is present the separation of variables method with a little bit of context up front. So let me start with that and just remind you what it was like to solve a matrix equation or a vector equation. Derivatives of some time-dependent vector x is equal to a matrix multiplied by that vector. So the method that we used here was that we found the eigenvalues and eigenvectors of the matrix A, and we assembled a sum of those vectors scaled by their eigenvalue in the power of an exponential. So we have, let's say, an arbitrary constant multiplied by e to the first eigenvalue t, and then that gets multiplied by eigenvector 1. And you'll notice eigenvector 1 is just a fixed geometric object. There's no time dependence, so there's no of t that I should put in there. The time dependence and the geometry are separated. And then we added up a whole bunch of these. If our matrix was an n by n matrix and the vector was an n vector, then we would have n of these, and we'd have a sum of these arbitrary constants with the appropriate terms all added up. And the nth eigenvector there at the end. And that was the way we solve these matrix equations. Okay, so the lambda are the eigenvalues, and the v's are the e vectors, the eigenvectors. All right, so when I presented, and earlier in this playlist, I did it this way. Solving the heat equation can be done in a really similar, analogous way, taking advantage of eigenvalues and eigenvectors, but here, instead of having vectors as our object, we have functions. So, in other words, u is a function of t, as was x, but now it's also a function of x. And the operator is no longer a matrix operator, it's a differential operator. But the idea is still pretty much the same. What we do is, instead of finding eigenvalues and eigenvectors of a matrix, we're now finding eigenvalues and eigenvectors of an operator, and we assemble the solutions in the very similar way. We write these as sums with a cj e to the lambda j times t v, and now instead of v sub j with a bar over top, it's the function vj of x, where I've replaced the vector geometry sort of component with a function, but still the time has been separated out in this exponential factor in front. And here we still use the same language. Lambda j are the e values, the eigenvalues, and the v. So these are sometimes called either eigenvectors, which is a sort of generalized notion of vector to include functions, or sometimes they're called eigenmodes, and sometimes they're just called eigenfunctions, which is probably the most descriptive and familiar way of describing what those are, because they're immediately recognizable as functions. So where do we find the lambda j and vj of x? So we find these by solving an analogous equation to what we do in the linear algebra context. We solve the equation, instead of a times x equal lambda x, it's the differential operator equal lambda x, or lambda u in this case. And that's just like ax or av equal lambda v. But we have the added the added feature of having to satisfy boundary conditions because this is a PDE. Okay, so this is really similar, except we're now dealing with functions instead of vectors, but the calculations really run in a very similar way. And what we find is that the Vj of x are either equal to sine n pi x over L in order to satisfy, let's say, Dirichlet conditions, or they're equal to cosine n pi x over L. I guess those should be j's. Let's see. Yeah, so to be consistent. Oh, maybe it's easier for me to just make those that j and n. And this one, the cosine, is when you have Neumann boundary conditions. Okay, and then other boundary conditions will give you other eigenmodes or eigenfunctions, but these are the two most common ones. So what about if you're solving a wave equation? So let's say we have u, and I'm going to use subscript t to denote derivative with respect to time, just to keep my notation concise. And so that's utt equals c squared uxx. That's the wave equation. Or more complicated, linear, and it's important that they're linear, other linear PDEs. This idea works in general, but it becomes, well, arguably easier to solve the eigenvalue problem by kind of ignoring the eigenvalue problem and using something called the separation of variables. So just to clarify, the reason we need linear is because that gives us superposition. And once you have superposition, if you can find eigenvalues and eigenvectors, then those are sort of simple cases to solve, right? We were able to solve for the eigenvalues and eigenvectors in these boundary condition cases pretty easily. And then you multiply it by the exponential factor, and once you have, if you have superposition, you can add those up and be sure that you're still going to have solutions to your original equation. Okay, so let's now go over to the separation of variables method itself. So the separation of variables method. So I'm going to solve the wave equation here specifically, but in a lot of courses you'll see the diffusion equation is solved using this method without any discussion of the eigenvalue eigenvector structure to it. Now the wave equation, so let me just write that down again. It's u sub t twice equal c squared u sub x. But because there's two derivatives in space and two derivatives in time, we need a whole bunch of conditions. So I'm going to keep a guitar string example in mind. And so for a guitar string, you would impose that the position or the deflection of the string at the origin at x equals 0 should be 0, and that the deflection at L should be 0. In other words, your string is pinned down on either end. It doesn't move up and down at all. And what we'd like to do is we'd like to find the position, the deflection of the string at position x in time t as you play a guitar, or even just as you strum once and watch the string vibrate. Okay, so the method is to assume that x and t can be separated. So what I mean by that is, just as we saw with the eigenvector case, we saw that the functions that we were looking for, the basic components of this sum, could be written as a part that's time dependent and a part that was just geometric. Or with the diffusion equation, it was a part that was time dependent and a function that was independent of time, just dependent on space. So that's what we're going to do here, except the tradition is not to assume that it's an exponential time dependence, even though we'll find that it is as long as you allow complex values of the exponent. But what we write instead is we just write the time-dependent part as an unknown function y of t, and the space part, just as we did with the heat equation, it's a v of x. And we expect that y of t is going to look like e to the lambda t, but we're not going to assume that up front. And what happens in a lot of these cases is we don't quite get exponential alone. We could have a complex eigenvalues, in which case the function y of t could be exponential or cosines or sines or exponential times cosines, any of the things that we saw with second order ODEs. Okay, so once we do that, we're going to plug that into the original differential equation. And what we get then is, and I'm going to denote derivatives with respect to t by dots. So when I take u sub t, I get two derivatives in time, so I'll denote those with dots above, of y of t. And I can do that with just a simple notation instead of a subscript t because y is only a function of one variable. And the v of x is a constant with respect to time. And similarly, y doesn't get influenced at all by that space derivative or the two space derivatives, but v does, and I'll denote space derivatives with primes. So what the wave equation says is that y double dot, and I'll suppress the arguments and we'll just have to remember which is a function of t and which is a function of x, is y double dot times v is equal to y times v double prime. Now, this is no simpler than the wave equation. It's just a restatement of it with a few more variables involved. But if you notice, we can separate these and write the equation out in this form. And now I'll put in the t again because it's important for the next line here, the next comment. And that is, here we have, on this side, we have a function of t. And on this side, we have a function of x. Well, if you change the t value, you think this one might change, but this one doesn't because there's no t in there. And similarly, if you change the x value, the right-hand side looks like it might change, but the left-hand side can't. So what you conclude from that is this is equal to some constant, and I'll call it alpha. People often use the letter lambda there, but it's deceiving because alpha is not going to be the same as the eigenvalue lambda. So that's why I'm going to stick with alpha here. Okay, so from these are two equations, right? We've got a y double dot over y equal alpha and v double prime over v equal v. And so I'm going to write those out separately. So here are two equations that we get. C squared v double prime equal v, and y double dot equal, oops, I forgot an alpha there, alpha v, and y double dot equal alpha y. Okay, so this is the basic formalism of separation of variables, and for any PDE, this is the way you carry it out, and everything that goes on from here down is going to be somewhat specific to the wave equation, although the methodology will remain the same. Okay, and as a general rule, it might even make more sense to call this the separation of time and vectorness, because this kind of is what we've been doing all along, right? When we talked about the matrix equations, we were separating time and vectorness. In the heat equation, we separated time dependence and vectorness. And again here, we are separating time and vectorness. But when I say vector, I'm including the idea of a function as a vector. All right, so now we've got to set about solving these two equations and seeing what our solution can be composed of, and then superimposed to get our final general solution. So here I'll flip to the next page, and we will start with c, whoops, that should be a pen. So we'll start here with c squared v double prime equal alpha v, and I'll wait on the y equation for now. So there are three possibilities. Alpha is just a constant, but we get three distinct cases when alpha is equal to 0. That means that v of x is equal to, well, if the second derivative is 0, that means this has to be a linear function, so I'll call that a plus bx. And if alpha is, let's see, I'm going to need a little bit more space here. If alpha is positive, then v of x is going to be equal to some constant times e to either plus or minus, because once you take two derivatives, the minus sign will disappear, the square root of alpha times x. So that satisfies the equation where when alpha is positive. Both of these, or you can sort of think of it as all three of these, right? There's a constant solves this one, a constant solves the alpha equals 0 case, and then there's two here, I guess. There's four, I suppose. But none of those will do very well at satisfying the boundary conditions of a guitar string, which is pinned down and doesn't move at all, so u has to be 0 at the endpoints, right? This one here, the a, would correspond to a constant deflection. So you're just shifting the entire string up, which would break them. This one, you could anchor it at one end, but the other end would be dangling off in space. And these exponentials, those are problematic because you can't have a straight string on a guitar that has, or you can't bend a guitar string with an exponential shape without one of the ends blowing off the guitar. Okay, so the only one that's going to work for us is going to be alpha negative, and in that case we get well, actually, let me do that with a little bit more room. So I'll just leave these here as not going to work. And then when alpha is negative, what do we have? We've got c squared v double prime equal alpha, but remember that's negative. Oh, actually, let's flip it over to the other side right here. So that's now going to be a positive. This is a positive coefficient in front of the v equals 0. And when we have a positive coefficient like that, we get a frequency, and I'll just call it omega for now. And omega is going to be the square root of minus alpha over c. And that gets put into our cosines and sines. So v of x is either cosine of omega x or sine of omega x. Now, if we're solving the wave equation, the cosine has, if that's going to change in time, that you're going to have the ends of the cosines are, at least at the origin, it's at 1, and that's not a very nice guitar string because it's going to be floating off your guitar. So this one is not going to work for our boundary conditions, but sine of x can be 0 at the origin and somewhere out along the guitar string. So, and remember, did I write these down explicitly? Yeah. I wrote down our boundary conditions here, and we could plug those in and see when the sine function works. If I plug in the cosine function, it just doesn't work at all. But if I take v of 0 using the sine omega x, we get the sine of omega times 0, which is just 0, and that worked right away, no problem. And then if we plug in L, we get the sine of omega times L equals 0, which means that we have to choose omega L equal n pi, and that tells us that this frequency omega has got to be n pi over L. So we now know that our v of x's, we can put a subscript n, we have a whole list of them, and they are going to be sine n pi x over L. All right, so that gives us our modes, and those look like this. They have to go through 0 at either end. Sine n pi x over L when n is equal to 1 is just a half wave that goes from 0 to L. When n is equal to 2, it's a full period. When n is equal to 3, it's a period and a half, and so on. So there we have n equal 1, n equal 2, n equal 3, and that keeps on going. So all of those will be reasonable solutions. We call n equal 1 the fundamental frequency, or the fundamental mode, and then the other ones, with a guitar string, at least in the music context, we call those overtones, and sometimes you'll hear them referred to as harmonics. All right, so we still have to figure out what the time dependence is, and that comes from the y equation. So y double prime is equal to, and now I know that alpha, oh, I didn't write it down here, but we had that alpha is related to omega by this expression here. So if I solve that for alpha, I get alpha, oops, I get alpha equal minus c squared n squared pi squared over L squared. And so that means that I have minus c squared n squared pi squared over L squared multiplied by y. And now you'll notice this is definitely a positive quantity with a minus sign out in front. So I have all these are squareds and there's a minus sign out in front. So that means that I'm going to also be dealing with cosines and sines in time. So we have the corresponding yn of t functions will be some combination of a cosine and a sine. And I didn't mention the initial conditions yet, but the initial conditions are going to be how we decide on whether to have the p sub n's, the q sub n's, or both. So that is our time dependence. Now these clearly do not look like e to the lambda t, but if you think of these cosine and sines as having come from e to the complex lambda t, then we can assume that lambda must have been equal to cn pi over L times I. And so if we had gone with an e to the lambda t approach, this should have emerged as our conclusion on what lambda value we must have. Okay, and that's a whole sequence of lambda values. So now we can put together our general solution. And the general solution is going to look like this. It's going to be u of x and t equal sum from n equal 1 to infinity of Pn cosine Cn pi t over L plus Qn sine of Cn pi t over L. And all that gets multiplied by the eigenmode sine of n pi x over L. And that is our general solution to the wave equation with Dirichlet boundary conditions. And what we need to do now is just figure out how to solve the initial conditions. Wave equation with Dirichlet. Now, if I had a context where I had a wave equation with Neumann boundary conditions, I would have ended up with cosines here, but the rest would come out very similar. Okay, so maybe I'll hold off on the initial condition discussion for a subsequent video.